Thanks for coming back. This session is really exciting. There are really good talks. First one is by Patrick Wendell, who's one of the co-founders of Databricks, and he's going to talk about Spark's performance. In particular, before this thing that he's going to present, we only had unit tests, but with this now, we can actually test, how much is the performance of Spark changing with, each commit that's coming in. So please go ahead.
Thanks a lot, Ali. So I'm going to get started. I'm going to talk about performance in Spark today. A little bit about my background. I worked on a bunch of performance benchmarking. Maybe turn the mic down. I think it's some reverb a little bit. I worked on performance benchmarking in Spark, and I co-wrote with Andy Kowinski, who's kind of the MC in the other room, the Spark Perf, which is a set of utilities we use to do QA for Spark releases. And I also wrote a lot of the UI and instrumentation inside of Spark now that gives you information about performance. So I've kind of done quite a lot in this space. This talk is really focused on helping existing users of Spark, or people who think they will become users of Spark, get better performance out of their applications. And because I know these things tend to get put up online and then referenced a lot, this is current as of Spark 8.081, probably also as of Spark 0.90. And if it's like 2 years from now in 2015 and someone's watching this online, this might be totally irrelevant. So I just want to qualify that. If you're a newer user to Spark, you should still be able to get a lot out of this talk, but I'm going to move at a pace where I kind of expect that you've seen the API and you're kind of familiar with Spark already. So what I'm going to do first is give a deep dive of how Spark's execution engine works internally, because that's the best way to get good performance out of something, is to understand what's going on under the hood. I'm next going to explain some of the tools we have now in Spark for doing instrumentation of your jobs. The Wi-Fi isn't working so well, so there's a tentative demo as part of this. And finally, I'm going to go over common mistakes I've seen people make when writing Spark applications that cause bad performance. So why do we care about performance in the first place, and why do you want to sort of go deeper in your understanding of Spark? I'm going to give an example here. So let's say you have an RDD, and it's composed of tuples or pairs, and each pair has a person's name and then a transaction amount. So first Patrick spent $24, and Matei spent $30, and then Patrick spent $1 again. This is a kind of big, maybe you have a huge set of billions of these transactions. And all you want out of these is to get just the total amount of dollars spent per each person. So you really just want to do a sort of aggregation operation. Well, one way to do this in the Spark API would be to take your RDD, to call group by key. That basically gives you a big sequence of all the values associated with one key, and then to do a sum over that sequence and collect the result. That is correct way to do it. Another way is to use the reduce by key operator in Spark, where you give it a reduce function and you say, okay, what I want to do with the values for each key is a reducible type of operation. It's something that's associative and so on. And so I'm going to give you the function. You just add up any two values, and eventually you'll get out the right value at the end. And these two, though kind of nominally they have the same properties, they actually will produce very, very different types of performance. The group by key operator in Spark completely shuffles all of your data, because the semantics here are that for each key, you'll get the entire list of values associated with that key, and then you can do whatever you want with them. Whereas if you use reduce by key, it will actually do a local reduce on each node before it shuffles the data. So this is similar to what's called a combiner in Hadoop, except we can do it in Spark automatically for these types of operations, because we have the closure that you're running. So a naive implementation might suffer by like 10 or 100 times if you don't really understand what these API calls are and how they're different from each other. So in that spirit, I want to start the talk by looking under the hood and kind of explaining how Spark works internally. So this slide is going to have the high-level concepts in Spark, and by no means do I expect you to understand everything. But the basic way, the key abstraction in Spark is this resilient distributed data set. It's essentially a big parallel collection of objects with partitions. So the objects are sort of partitioned into different smaller subsets. A user application in Spark will create RDDs, do transformations and actions on them, and that's kind of the main way you interact with data in Spark. But under the hood, these result in a DAG of operators, and that DAG is compiled into something called stages, which are the unit of physical execution. So whenever you see metrics in Spark about, this stage finished in this much time, a stage is what you really see on the physical side. And then each stage has a series of tasks, and there's one task for each of these partitions. So, this is a lot, but eventually if you come to a solid understanding of all these concepts, you'll be in a really good position to debug Spark performance. I'm going to give an example. So let's say we're just doing some analysis on a text file, and we'll actually do the analysis I said before. We're going to parse the data, and then we're going to do a big distributed reduce operation. So the first thing I do is I call a spark context.txt file, and I give it some HDFS location where I want to analyze the data. And this already creates a logical RDD. That RDD is represented by this blue thing at the bottom. It's a big data set. It has sort of partitions, and those partitions are based on where the data is in HDFS. So now I map it, and I actually split each line by the tab character. I do another map where I just select 2 fields. These are really common types of data munging operations inside of Spark. And then I call my reduce by key, and I pass it a number of partitions to make in the new RDD. So what you can see is that each of these operations actually returns a new RDD in the kind of logical graph of what I've done in my Spark session. And there's 2 different types of RDDs here shown. One is this type where it just depends on its parent in a very obvious way. So if I'm doing a map or a filter, I can kind of do that in place. So the way that this depends on its parent RDD is kind of called a one-to-one dependency. It means that you can do this without moving any data. But when I do a distributed reduce, it creates it forces what's called a shuffle. So the way that this new RDD depends on its parent is that you have to shuffle all this data because now you've said that I'm going to get all of the values for one key in the same place. So as you're writing this code, there's like a logical graph of RDDs that's created. And then I collect it, which means I actually don't even want an RDD anymore. I want you to materialize some output for me at the driver. But what this gets compiled into by what's called the DAG scheduler, component inside of Spark, is a set of stages. So a stage is a set of a sequence of these RDDs that have no shuffle between them. So essentially everything between the shuffles can get coalesced into one stage. The reason, like the intuition there is that if you're doing a bunch of maps on the same data, there's no reason to sort of separately execute those. You can pipeline them into one task and run it on the partition. So I'll just show you what happens there is that this graph gets compiled down into 2 stages. And these stages are not exactly the same as the operators you used at the beginning. Each stage will have potentially 1 or more operators associated with it. So what is the semantics behind these stages in this particular example? Well, the first stage is going to collapse all the things we did at the beginning. So it reads the data from HDFS. It applies the 2 map functions where we were extracting the fields and whatnot. And then it will start to do the reduce, and it will write out the shuffle data at each partition. And on the other side, the stage is going to read the partially reduced shuffle data. It's going to do the final reduce, and then it's going to send the result back to the driver. So this program that I wrote would actually compile down into 2 stages, and that's what you would see if you looked at anything that showed you kind of instrumentation about your job. A stage itself is just composed of tasks, so you create a task for each partition. You serialize the task. This is what Spark does, so you don't have to do it, but this is what Spark's doing internally. And then it's scheduling the task and shipping it to the slaves. What's happening for each task is, so task execution is kind of the fundamental unit of work in Spark. Everything going on inside of a slave node is just executing a task at any given time. And what a task looks like is it fetches its input. So we showed that you can do a shuffle in Spark. So the input to the task might be just the output of the last stage. The input to a task also might be an in-memory RDD. It might also be just a file in HDFS or in any other input format. It executes the task, and then it writes the output, which could be, again, intermediate shuffle output, or it could be writing something back to the driver, or maybe you're saving a file to HDFS. But this is totally pipelined in Spark. So for example, if you have a lot of input data to fetch, Spark will start processing the input data before it's finished fetching it, and will do likewise for the output data. And if you look at a Spark Executor, which is the name for the slave component in Spark, all it's doing is it has a series of cores, and each core is doing this kind of embarrassingly parallel task execution. So each core is just fetching some data for each task, executing the task, and sort of passing it on to the next point in the chain. And this should be your mental model of what a physical execution looks like inside of a Spark executor. So just to summarize some of the things we talked about, a task is the fundamental unit of work. A stage is just a set of tasks that run in parallel and have no dependencies on each other. The DAG, this is kind of going bottom to top, which is the opposite of how we went the first way. The DAG is the logical graph of operations that occur as a result of you mutating these RDDs. And the RDD is kind of the basic abstraction in Spark where you have a parallel data set on top of which you can do operations. So now I'm going to show you Wi-Fi permitting the UI that we've written inside of Spark to give you more insight into the performance of your application. And since you have at least some familiarity with what tasks and stages are, the information in this UI will hopefully make more sense. So what I'm running on this cluster here, dun, dun, dun. All right. Okay, yeah, it seems kind of to be working. So this is a cluster running Spark, and this is the default UI that comes up inside of a Spark context. There's many tabs here. I'm going to go through kind of how I would walk through normally if I was trying to assess the performance of this job. The first thing I look at is go and see what executors are running. So if you get bad performance, one way to get really bad performance is you thought that you had 10 slaves in your cluster and you actually have 2 slaves because you messed up a config file or something didn't start correctly. So I usually first just go and see, okay, do I have all my executors and how does everything look on these? You know, are they running tasks and do they have data in memory, et cetera? But if that all looks okay, I actually go and look at the stages. And this will show you kind of active and just recently passed stages that are running, and it'll give a lot of information about them, just even in this summary view. So one thing is you have the name of the stage, and we name the stages by the action or shuffle barrier that caused that stage to need to exist. So it'll actually give you the line in your code where you called something that caused this stage to happen. That helps a little bit, helps you associate what data is happening with which inputs. So let's look at what we have here. So we have the stage, we have how long it's taking and how many tasks are in it. And then we also have the amount of data that it read or wrote if it's a stage that was participating in a shuffle. Might be able to make this a little bigger, but there's many columns, so might have to retreat. So let's look at actually what's inside of one of the stages. So if we zoom in on a stage, the first thing we get is these nice summary metrics that tell us kind of how things did it in a sense of a distribution. So what we can see here is for the duration of each task and the amount of shuffle data written, kind of what was the maximum, minimum, and average. And what you really want in these distributed processing frameworks is you want things to be fairly uniform. You don't want there to be one task that took way, way, way longer than the others. So what you typically compare is something like the median to the maximum performance in a particular stage. And this is maybe 3 times faster. That's actually not that bad. What you really don't want is maybe 10 or 100 times faster for your maximum than the median. But then in addition to the summary, we can actually get a breakdown of every single task, whether it's currently running, how long it ran for, where it ran, and then these nice other metrics that we have over here. And one thing that's pretty cool is you can sort this table. So almost always the first thing I do when I'm looking at a particular job is I sort and I say, okay, show me the task that had the worst performance. Show me the task that took a really long time to run. I want to go see if there's anything fishy about those. Because if you look at the very worst tasks and they actually look totally fine, then probably your job is doing pretty well. So I just sorted by duration because all of these fields are sortable. And I see, the longest ones are around 3 seconds, which isn't that bad in this case. But I get some hints as to why things might take longer than I would expect over here in these other columns. So one thing it will tell me is how much GC happened inside of this task. So in Spark, GC can be an issue. And this will tell you quickly if GC is an issue for your particular job or not. Because it's also a good red herring since you think, oh, it's JVM, probably I have a GC problem. But you don't always have a GC problem. So this will show you if that's an issue. And then it will also say how long it spent writing the output. During a shuffle, it actually has to write the output to disk, and this keeps track of how much time in the total life of the execution of the task was spent blocking on these writes. And we see that here actually there's some issues with that, and that's what most of the time in this task is lost to, is just writing its output. So we might want to look at whether that's going to buffer cache or whether our disks are set up correctly or something like that. And I'll talk about that a little more in the next part of the talk. So the last thing, if this Wi-Fi is working, that I will look at is look at the in-memory data sets and make sure everything looks okay there. This job that's running is actually just running many times a repeated iteration on one data set, so all I have is one RDD. But one thing that's nice to verify is that I want to make sure the whole thing is in memory. In some cases, you might not have enough memory in your cluster to support this, but that will affect performance. So if you're looking at a particular stage and say, no, this isn't performing so well, a good thing to look at is, are all the inputs to this stage in memory, or if they're not, sort of do I understand why that's happening? So this is a single RDD that happens to be cached, and it is 100% in memory. And I can even get kind of a drill down of what's the distribution of data over nodes, because you don't want to have one node become a hotspot. And it can tell me for every partition of the RDD how big is it and where is it replicated. It may be on more than one node. So this is like a really quick overview of the performance instrumentation we have inside of Spark. There are some things that we haven't done yet, which I'd like to work on for Spark 0.9 or maybe 1.0. And the biggest thing is we don't instrument the read side of the shuffle yet, we only instrument the write side. So there's a big shuffle where you move a lot of data, and we keep track in pretty fine granularity of how efficiently we're writing the data out, but we haven't done the same for reading because that code path is much more complicated inside of Spark, but look forward to that in a future release. Okay, so I've told you a little about how Spark works and how you can kind of look around inside of Spark and get a sense of whether your job's running well. What I want to finish the talk with is a bunch of different problems I've seen people have, kind of common things that I've seen come up many times that cause their applications to perform much worse than they could. You can kind of divide these into different categories. So where can your thing possibly run slowly? Well, one is that it can run slowly when you're scheduling and launching the task. So this is entirely at kind of the driver program where you're actually calling Sparks, calling map and reduce, et cetera. And another place is when you're executing the task, it can go slowly. There's also this big shuffle that happens where you move data between stages. That can go slowly. And lastly, when you collect the results, there can be problems. So I've sort of divided up common things I've seen along these categories so that you can get a sense of like where it's happening inside of this broader computation approach that is inside of Spark. Okay, so the first thing, so scheduling and launching tasks. Well, one of the most common things I've seen people do is they include a really huge object inside of, they keep a reference to a big object inside of a task, and that causes the overhead of shipping tasks to become much higher. So in this example, I have a hash map. This is kind of Python-ish code, and then I call a map function on my RDD, and what I do for each item in the RDD is I look up its value in this big hash map, and then I do a count of like kind of a histogram of all the values. And this is a good idea, and a lot of code looks like this, but if that hash map is really massive and your RDD has maybe thousands or hundreds or tens or hundreds of thousands of partitions, you're going to be actually serializing and creating a copy of that hash map for every single task that you send out. Because remember, we send out one task per partition. In general, Spark can actually handle a lot of tasks and can launch tasks really quickly, but you will hit some overhead at some point. Like if you want to launch 100,000 tasks in a second, it's not going to work if your tasks have a 1 megabyte hash map inside of them. So there's a few ways to fix this. So I guess the first thing is, how do you even know this is your problem? So we actually added a warning for this that's in 0.9, and it will tell you, hey, your task is really big and it might cause problems. But the way to fix this, there's two ways. One is you can use something called a broadcast variable, which is we have built support into Spark for broadcasting large objects in a way that's more efficient than just a one-to-many shipping of these objects. You can also make your big hash map or whatever into an RDD itself, and then use join and cogroup and the other operations inside of Spark to actually do this in parallel, so you're not sort of just replicating the thing many times. Another issue I've seen is having a large number of kind of empty tasks, because you start with a big data set, you filter it, and you do a high selectivity filter, and then you have a bunch of kind of null tasks where the filter didn't actually return anything. So a good example is I start with some S3 data set, I split out the fields, and then it's a whole year worth of data, but I'm only selecting from these fields one day, October 17th, and one particular hour. And if the underlying data set has maybe 10,000 partitions, your data probably is only in 2 of the partitions, depending on whether the data set is sorted or not. And then you do some subsequent processing. But what happens is you end up with all these kind of empty tasks that are doing nothing. The way to see this is that you'll have a lot of tasks that do nothing. They like write no data. They take maybe 10 milliseconds or 5 milliseconds to run. And you can fix this by actually explicitly coalescing your data set. So there's operators we've added called coalesce and another one called repartition. And you can essentially, I know this is down low, it's kind of hard to see, but all this does here is it calls that operator before it continues to process the RDD. And this reduces the number of partitions. So that's basically a direct way to fix this. So what about when your tasks are executing? One thing I've seen a few times is people will execute tasks using a map function, but there's a huge overhead for each record. So let's say I have my RDD and I want to call a map on it. And what I do for the map is that for each object in the RDD, I create a new connection to MongoDB or some random storage layer, and then I write out to that storage layer, and then I close the connection. So this is going to yield really bad performance because it's reinitializing this connection every time you process an object. If you have billions of objects, things are going to go super slowly. detecting this, well, it's hard to really have a good way to detect this other than just seeing that the task is much slower than you might expect it to be. And to fix it, we have a function called map partitions where you can do this overhead one time for each partition of data. So in most cases, you might have way fewer partitions than you have records. So maybe billions of records and only a few hundred partitions. So you can kind of initialize the MongoDB cursor or whatever it is one time. You can write out all your data, and then you can close that. In Scala, we also have this thing called map width that uses some nice Scala language features to make it a little bit more elegant. But it's totally achievable in Java and Python using just this thing, map partitions. Okay, so another problem in Spark I've seen is skew between tasks. This is a really common problem in any data parallel framework, including Hadoop. To detect skew, what will happen is if you sort your tasks by response time, or you look at the histogram, you'll find out that the 99th or 100th percentile behavior is like 100 times worse than the average behavior. And this means that you have a problem. The best way to fix this, well, this is always easy to fix, but there's different types of skew. So one type of skew is that you have data skew. So a good example is I'm doing a group by, and I'm aggregating a bunch. I'm going to add up the total amount of revenue I had per zip code. And it turns out that the New York area zip code is so massive, and this is such an expensive calculation that that one reducer that has that particular key on it is so overloaded that it's like running out of memory, or it's just going really slowly compared to other things. That's not a super easy problem to fix. There's algorithmic approaches to doing intermediate aggregations. Like first I aggregate by hour and zip code, and then I do a final aggregation. You'll have to kind of rewrite your job. There's not a way to natively support that in Spark. But you can also consider just a different way of parallelizing your algorithm. See if there's some other way you can do it. Because really the problem you have here is that the algorithm you've presented is not especially parallelizable. These are both kind of crappy answers because there's not great answers to that problem. Another issue is worker skew. So I have some slaves where the OS is having some crazy problem, and all of the tasks that are on this particular slave are really slow. The good way to figure that out is when you sort by duration, you find that the 50 slowest tasks all happen to have run on the exact same node, and there wasn't some other intermediate variable like garbage collection that caused them to be correlated. It's just that this node is kind of wonky. There's a few ways to mitigate this. One is you set spark.speculation to true. So this tells Spark, should I do speculative execution inside of the scheduler? This is actually disabled by default, I think, in Spark, unlike in actually, I don't know if it is or not in Hadoop, but so you need to explicitly go set it. The obvious long-term answer to this is keep an eye on nodes that are crappy in your cluster and just remove them. Spark is fault tolerant. If you remove the node, it will continue to live on and you'll get way better performance. Okay, so now writing data between stages. So the number one problem I've seen here just recently, so maybe I'm somewhat biased because we've been seeing this problem in some recent performance work we've been doing, is that you don't leave enough buffer cache in your operating system for these intermediate outputs to be written to memory instead of to disk. So Spark actually writes shuffle data to the buffer cache right now. That's something that may change in future versions, but essentially we're relying on your operating system to store this data in memory during the shuffle. The reason why we do this is because we expect the intermediate outputs could be bigger than you have memory for, so we don't currently store them in memory inside of Spark, but we might do that in the future. So to detect this, you just look and say, am I spending a lot of time writing data inside of my task? There's a UI hook for that, so it should be pretty straightforward. And to fix this, it's just if you have a workload where you're doing huge group bys and very large shuffles, leave space for the operating system to use up the buffer cache. If you just don't use that space in the JVM, the operating system will start to use it. A rule of thumb is you might want to leave as much as 20 or 30% of the space free if you have a massive heap. It really depends how much shuffle data you're writing. If you're not doing jobs that do big shuffles, then no reason to give up that space. But if you are, for now, you should leave space for the OS. Another problem is that people don't set the location where Spark should write its shuffle data to. So this is basically where it writes to all its intermediate data. And again, sometimes it's not going to be in cache. It will go to disk. And if it goes to disk, you want it to have high throughput. So the default here is to write to /temp. That's going to give you really bad performance because it's probably just one random disk that is also the disk the operating system is using, depending on how your thing is configured, how your machine is configured. But the kind of best way to do this is to have multiple disks on the machine that are either dedicated to Spark or shared between maybe Spark and HDFS, but they're used mostly for for storage, and to give a list of these locations on these disks to Spark, and Spark will kind of stripe the shuffle data across them. This is, I think, exactly the same thing that Hadoop does. You also might want to mount these drives with the extra mounting options that say, these mounting options basically tell the OS not to try to do a disk write to record the access time every time you open a file, and that just causes extra seeks. Okay, I'm almost done here, but the last couple are not setting the number of reducers correctly. So this behavior has improved a lot recently in Spark, I think as of maybe 0.9. I don't know if it made it into 0.80, but we now do a better guess at how many reducers we should use if you do a big shuffle, but you can still have problems, and the problems can go in either direction. There's not a hard and fast rule here, so I'm just explaining the trade-offs. If you have too many reducers, you'll have this issue where you have a lot of tasks that are doing very little work, and the overhead of launching tasks becomes pretty high. So this is also a problem in Hadoop, but the kind of threshold where too many tasks is a problem in Spark is like tens of thousands or hundreds of thousands. In Hadoop, it's much, much lower than that. So actually, all else equal, you should bias in Hadoop towards having, or in Spark towards having more tasks than you might use in Hadoop. If you have too few, you don't get any parallelism in your cluster. So if you use one reduce task and you're doing a huge aggregation or a join or whatever, it's all going to go to one node, and you've sort of completely lost all the parallelism. And the very last thing I wanted to say is, this is a fairly straightforward one, but if you have a really big data set, you shouldn't just collect it on the driver node. That's kind of the master node of Spark, because it's going to run out of memory. You should try to actually use Spark to do whatever you're doing with data, either storage or processing. I'll just see sometimes on the mailing list someone says, oh, I had this big HDFS file, and then I called collect on it, and like my driver node ran out of memory. Well, that's happening because this file is maybe huge, and your driver node is just one node in the cluster. The right way you want to work with data in Spark is to actually use Spark's operators, group by and join and filter or whatever, to do what you need to do. And then even like writing it out to disk can often be done in parallel by saving it to HDFS or a database or whatever. Okay, last slide is just some advanced profiling techniques. I'm not going to go into this in detail, but these are things that I've used to do profiling that's beyond what we give you in the Spark UI. Some of them are, if you go onto this, almost all of these are things I do. I log into a slave node while a big job is running, and I run these. So JStack and JMap will give you really quick insight into what's the stack trace of the JVM right now, and what is the current sort of makeup of what's in memory. And there's these other utilities like dstat and iostat and LSOF, which can give you they're sort of just OS utilities that give you information about what's going on in the machine. Are you totally utilizing the disks 100%? Is the CPU 100%? You want to see, is there a bottleneck resource in here, and what is it? Okay, cool. So I'll just, in conclusion, say we really expanded the support a lot in Spark 0.8 for doing performance monitoring, and I kind of walked you through the UI for that, and I think this will be a big difference maker for people who are running Spark programs. There's just way more insight into what's going on. Also, the more you understand about Spark and how it works internally, the kind of better you're going to be at debugging performance issues. That's true universally about any system, but it's definitely true about Spark, and we're trying to make it easy for people to learn the internals pretty well. Okay, so that's it, and I don't know if I have time for questions, but thank you. Do I have time?
Questions?
How can I access the data I can see in the web interface via API? Like if I want to integrate it to my monitoring system?
Yeah, that's a great question. So for some high-level metrics, we actually... Oh, okay, I just need the mic. Is that okay?
Why don't we switch that?
Okay. For some aggregate metrics, we currently actually have a metrics library where you can, I don't know if you've heard of the Coda metrics library. It's this way to interface with JMX and Ganglia and all these third-party systems. We currently report those in Spark. So there's a doc about Spark metrics you can look at. For the very fine-grained metrics about this task, right now we don't expose those externally, but we will in a very upcoming release right now. Yeah.
Okay, let's thank the speaker.